Longest substring without repeating characters. Given a string S, find the length of the longest substring without repeating characters. And a substring is a contiguous, non-empty sequence of characters within a string. What that means is if you've got, where is this? If you got a string A, B, C, D, 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 whatever, ABC is a substring, CAB is a substring, but BAC, so like that is not a substring, that is a subsequence. And we specifically need a substring. Okay, so this problem is, I think, pretty straightforward. The main key is knowing the right data structure for the job and being a little bit familiar with sliding window. So for example, okay, non-repeating characters. What that should suggest to you is some kind of hash set. Either a hash set or a hash table. Now usually hash tables are kind of a superset of hash sets, but it might be more than we need at the moment, because we just need to know if a character is being repeated in our window or not. And in C++, that is called an unordered set. So I'm going to go ahead and declare one of those. Unordered set. And what is it gonna hold? Probably characters. It's gonna hold characters, and I'm gonna call it scene. Or I could call it window. Let's call it window. The elements that are in our substring are gonna be in this window object. All right, a little bit more background about what a set is it's an unordered collection. Well, in this case, specifically, it's unordered. For example, in C++, you also have something just called a set, and that maintains an order. The difference between these in particular is unordered set usually is going to use some sort of hashing algorithm under the hood. The benefits of hashing algorithms are you can sort of calculate an index based on properties of the object, and it's like, in theory, if you take an algorithms class, they're going to tell you always assume a hashing, a hash set or hash table or whatever, anything hash based is going to be an O of n lookup time. So adding or removing or checking elements in the set is going to be O of n on the size of the table. But in reality, in all practical sense, some hashing functions are very, very good. The chances of collisions within that are rare. So it would be rare for one object and another object to come up with the same hash value. And what that leads to is you get O of 1, so a constant time for those same things. So we can check in constant time if a particular object is already in our set. Now, of course, these hashing functions, they're heavy-handed. They are like a high constant value, but it is still constant, as in it's not going to scale with the size of our input. So for most interviews, we're going to go with that. Sometimes you might get asked about that. I have had interviews call me out and say, like, hey, I don't think Python has a good hashing function. And I had to say, wait, after Python 3.4, they changed their hashing function under the hood to be more cryptographic. Cryptographic usually is it's a loose term. A cryptographic hashing function is not well defined, but it generally means the chances of collision are very, 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 very low. And it meets the requirements of certain popular standards to say something. This is secure, because security in cryptography is never foolproof. It's always probabilistic. So what's the probability of a collision? Well, it's below some certain threshold. So that's what it means for cryptographic hashing to be good, and languages like C++ generally use cryptographic hashing. That is a very long explanation for why we're using an unordered set. And the difference with a regular set is this is going to use a binary search-based thing under the hood. So it's going to generally have logarithmic lookup times and insertion, assuming you don't need to copy out the whole thing for additional, maybe the chunk of memory that you have allocated under the hood isn't big enough. You have to copy everything over to another area. If you don't have to do that, then it's going to be logarithmic for this and constant for this. So we're going to go with this, unordered. All right, so we have our window, and now we're looking for substrings. So we can do a sliding window approach. And what is a sliding window? It is a for loop. So for what? For what? I'm gonna use 2 pointers because our window has a beginning and an end. The window has, things come into the window and things go out of the window. So int L equals, I don't know, just the beginning of the array. L equals 0, R equals 0. And what else do I need? I need a return value. I'm jumping around a bit. So I'm going to make a return value because this is something that's going to be persistent beyond the loop. So int return int return. Started off as empty if our input is of size 0. So considering an edge case of an empty input, is that even possible in this? Yes, the problem states that it is possible for the input string to be empty, so we need to consider that. In which case our return value starts at 0. And then what do we do? So while. Yeah, let's make another variable. N equals s.size. So while r is less than n, increment. And so what's going on here is the right pointer is going to be stepping from right to left, and there'll be some condition. Sliding window generally has some logical reason why you might remove things from the window if it's dynamically sized. So we want the longest possible window we can find. So we need a condition for shrinking it, but on each step of the loop, we're going to increase it by 1. All right, so how does that work? Let's start with, I'm going to start with adding things into the window, and that's going to happen after the logical part. This is more straightforward, and we'll get into like the most important lines in this algorithm in a moment. So insert window dot insert s of r. And then we're going to set our return value. So return equals, I think you're going to get some kind of compile error if you, so this dot size value returns like size t, or it might be like a 64-bit integer or something versus comparing it with integers. So I generally, instead of using like, it would be, okay, I'll write out what I'm thinking first. So max of ret or the size of our window. Because at any given time, the window is going to have non-repeating characters as a substring. So just the biggest size we see is going to be our final output. But you're going to get some compiler error here. So instead of using this syntax, I generally go with, let's see, window. If the window is bigger with a question mark, or sorry, Boolean condition, and then return question mark window.size. All right, so what does this do? This is, you have some Boolean condition and then a question mark. And if it's true, if this condition is true, then this is carried forward into the assignment. So ret gets equal to this. And if this Boolean condition is not true, then ret is set equal to itself. That's what this syntax means. And this is common syntax in quite a few languages. All right, so now we have our window growing. We have our adding, our updating the output value. I'm going to add a return statement. And now we need the important line. So we need to shrink our window. And to drive home this discussion a little bit, we need to think about what conditions in which we might need to shrink the window. So let's go ahead and use this as an example. Suppose that is our input string. And suppose our window is, we have, this. I'm going to remove some of these quotation marks. And then we have like this. And then suppose we have, all right. Suppose we're getting to the very end of it. So we have this in our window, and then this. Okay, let me make sure I get this example right. Suppose this is our current window, WKE, and we want to consider if we're adding well, I don't like this. Hold on. Here, I got a better one. No, I'm trying to come up with an example where we have something in the middle of our window, and then we find a duplicate of something that's previously in the window. So if we are here, and we have WKE in our window, and then we hit a K. We want to consider if we should add this second K to our window. Well, not only do we have to remove this other K in our window, but we have to move everything to its left. So then we have to remove W and K, even though we're just looking at adding this extra K. This is, and for this reason, we're going to use a while in our condition instead of if. So instead of like if, blah, 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 it's going to be while. So while our window. And the way you check if something exists in a C++ container, so unordered set is a particular type of container, and they all have very, very similar member functions you can do. You can insert, you can, well, some of them don't allow like indexing into it, so you couldn't do like window 5 because there's no order to the window. It's unordered. You can't do that. It's not possible. So that's going to throw an error. But you can still do something like window.find, because we want to check for membership, s.r. So while the potential new candidate character is in, and what find does is, if it finds it, it returns a iterator to it. Iterator doesn't mean much in an unordered set. They exist. You can iterate through an unordered set. It won't be in any particular order, so as long as that's fine. But all we care about is that it's not equal to, this is what it returns if it does not find the element, window.end. And this is an iterator to like one past the last element. This is generally what's returned when the element is not found. So if we do not return this ending iterator, it means we found it. So if it exists, what do we got to do? We got to shrink our window. We got to remove things out of it. So window.erase is the syntax, and we're going to erase SL. And then I'm going to post increment. So what this line does is we erase S of L, and then after that we increment L by 1. So while our right pointer is in the set, we keep popping things off the left, so the old side of our window. So in this case, in this example, it would run twice. We'd first, we want to check, okay, can we add this? Can we add a K? Can we add K to our thing? And we have WKE in already. Well, first, K is already in our window, so we have to remove W. And W we remember by this left pointer. And then the second time it'll move one over, and then L is going to be pointing to K, and then we remove K. And then our condition will be okay, and we can go ahead and add things back into our window and update the return value if it needs to be updated. And that's it. That's pretty much the entire problem. So I'm gonna go ahead and let's talk about runtime. So what is the runtime of this sliding window? Your target runtime is going to be at least O of n, because you're not changing the, you're getting some input string. There's no particular order to it. You're not looking at less than the entire thing. So you're looking at least O of n. Oftentimes, if a sliding window calls for something like a, what do you call it? A heap, a min heap or a max heap, where you're getting the smallest element in the window regardless of order at a time. Whatever, a min heap or a max heap have logarithmic operations, so you end up with O of n log n. That is usually the max. If you end up with O of n squared, you're probably doing something else, and it's not a sliding window approach. But in this case, our approach is O of n. So we're looking at O of n, time, and space. And the reason for that is, okay, our window, this is the data structure that could potentially contain the entire input in it. So that's O of n space. This is constant time to allocate that variable. This is we do n steps of this loop. So in order to stay within O of n, we need the contents of the loop to be constant within that. So O of n loop, and then so this while loop. This could happen more than once with any particular for loop step, but the number of times this will execute is still going to be no more than once per character, because we're always moving this left pointer iterator whenever it happens. So it's going to either be checked once and that's it, so that's constant, or it's going to be checked multiple times, but we're going to increment the left pointer. So this is summing O of n. So O of n plus O of n, not times. And then this insert, because it's a hash-based data structure, this is going to be constant time. And then same for this. This find is also constant time. Now this syntax, this same syntax varies widely on its runtime based on the container. So if it was done on a vector, that would be O of n. If it was done on a min heap or a max heap, it would probably be O of log n. But since it's on a hash-based data structure, it is constant. This is a constant runtime. And then this is a Boolean comparison and an assignment. So that's, and then this is just retrieving a member value. So that's not calculating it. So this is also constant. So constant plus O of n. So it's not affecting the runtime. So the total loop is like O of 2n, which collapses to O of n. So O of 2n becomes O of n. And then that's it. That's our entire algorithm. And okay, so we got our time and space complexity. And then for the example, let's go ahead and use the same example. All right, so we have, I'm gonna do brackets for the window. So right now, our window starts out as this. And we have our return value. All right, so we have our window. We initialize our return value to 0. And then let's go ahead and continue with this example, going through the loop. So left, right, while the right pointer is not at the end. Window.find. Is anything in our window? No, there's nothing in our window. And so we're going to go ahead and add something to it, and then update our return value. The window size is now, there's 1 in it. So we're going to update that. Okay, next loop. Move this over to the right. Is that acceptable? PW. Yes, W is not in our loop, so we're going to go ahead and update that. Move it over 1. Can we do that? Well, W was already in our loop. So before we can actually, before we can insert, we need to move this. So while W is inside our window, we're going to move the left one over. And then W is still inside the window, so we're going to go ahead and move that over there. And now we can insert. So that's in our window. Now we're going to update our return value. 1 is not greater than 2, so we're going to go ahead and leave that as is. All right, going to add K to our window, next iteration of the loop, because that's fine, there's no clashes. Return value, 2 versus 2, it's the same. Add E to our window. Again, no duplicates. E was not in our window. And now we can actually update our return value again, so 3. And next iteration of the loop. Can we add K to our window? Well, K is already in our window. This returns not the end iterator. So we're going to go ahead and bump that. And then K is still in our window, so we're going to bump that. Now K is not in our window. We can go ahead and add it. Added it. Update our return value. 3 is not greater than 2. Wait, scratch that. 2 is not greater than 3. That is the size of our window. So next iteration. Boom, EKW. 3 is, that doesn't change. And then boom, we want to look at this E. That is in our window already. So this condition returns something that's not this. And then we're going to go ahead and remove our leftmost thing. So we'll remove E from the window. E is no longer in our window. We can go ahead and add in the new element. And then we're going to update our window size return value, which is 3, still 3, so that doesn't change. And that's it. R is now at the end of the string. And that's the entire algorithm. Is that what we expected? Is that what makes sense from like a logical point of view? Because this is an invented one. In this, it's based on this example, which has a max of 3, and it doesn't look like it changes it. So P, W, K, E. There's 4 letters total, but there's never like 4 of them in a row. So P, W, W, that's not a string. W, K, E, K, that's no. K, E, E, K, W, E. No, there's no, it's definitely 3. There's nothing, there's no 4 long sequences of non-repeated characters. All right, that's good. I'm going to go ahead and give that a run for syntax. Cool, cool. And we're going to go ahead and submit. Nice. All right. And then last, we're going to check that off. And you folks have a beautiful evening.